We are connecting in just a few minutes. Okay, we are like doing some things in the lab or preparing the class.
I'm jealous.
Thanks. We were just wondering
Yeah, sorry.
if you're fine.
Hello, guys.
Hello. Hey.
How are you?
Good, good. You?
Oh, it's so
Oh,
cute.
cutie!
I fit inside. My head. Let me see you all. How are you?
Good, good.
Good. So as you can see, we're here in the lab. That is Giuseppe. Here is the machine. And Edu is smoking. Will come in a second.
I'm here.
Ah, you're there? Imagina. Okay, so what we want to do today is talk about the possibilities for machine design, and specifically for Academy guys, the requirements that you have for this week and how we are gonna organize ourselves. Then we will talk about how you can hack the 6-pack milling machine and some possibilities that we have been thinking about so that you can get some inspiration. And I would also walk you through a little bit the electronics so that you understand more or less how many inputs, outputs, motors, and this type of things you have, okay? So first of all, and I can hear myself with Edu's phone, is regarding organization. We have to make groups for this week, especially in Info Academy, so you won't be working alone because this is kind of like a big assignment. And we were thinking that it would be something like 2 or 3 max people group. You can organize, I think, we don't have to tell you how to do it, but probably what we will do is just put a spreadsheet or something like that in a second, and then randomly put you in groups, and then you will collaborate. Then the idea would be that you have to document this in a separate repository. So you have to another repository just for the machine, and you have to collaborate within your group to make to document this. And as well, you don't have to do everything, so you will have documentation in this repository plus on your own documentation. So whatever you do, so for example, imagine that you are in a group, David, Marco, and Armand, which is the first row that I see here. So imagine that Armand does the modeling, David does the electronic, and Marco does the coding. So each of you will do each part that you are doing in your documentation, but you have to have it well linked to the central machine repository. Then regarding the machine itself, you will have total freedom to do whatever you want. You don't have to even stick to what we have in this have done like with this machine, but we encourage you to do whatever you like, although But if you want to hack this machine, of course you can. So try to come up with an idea soon, and then make your own version of this, or whatever you like. Yes, sir. Ah, okay. And what else am I missing? With respect to timing and classes this week, today will be the only day that we will do something for this week, like a session. We will explain how the machine was designed and how it is in terms of electronics and everything. And regarding materials and supplies, let's say, we are still waiting for some components, especially the most important ones, like, of course, they're not here. So we are receiving some of them. We have here like a lot of drivers. We have like, I don't know, tiny electronic components and stuff for the boards, but not the most important things. So we expect that for next week, we will have at least the most important parts. And as you know, of course, we have acrylic and nuts and everything in here. So for that, you don't have to worry. I don't know, Edu, you want to add anything?
Yes.
I want to. More or less close echo. I want to point that not having the components are like 95% of them arriving actually next week. Actually today I received 2 packages this morning. So the components will be here mostly at the end of the week. That doesn't mean that you cannot design. Actually, you have seen the whole design of the machine has been closed and completely done. Of course, it's not the same. It's not the first time we make a machine, and we know exactly where we need to put some things, etc. And sometimes it's easier to prototype. But actually, in this machine, we have seen through the years, like clearly, that spending more time in the digital and checking everything, checking the assembly, checking all the screws, check if you can put the screw in the 3D model, and check for the assembly order is much more important than prototyping and just jump really fast into prototype and make like 5 mock-ups of the machine. So actually, as long as the components arrive, we want you to do the design completely, check the software completely. Maybe you need to modify the firmware of the machine to match your needs. And that part could all be done on the computer. Let's say fabrication-wise, actually, there is a big mistake in prototyping, that prototyping needs a lot of handwork and jumping directly into the machine. Actually, it's not like that. It's much better to spend 1 more day in the computer fixing and checking things than trying to make 5 prototypes because you didn't check if the screws could fit, etc. Say that for this assignment, we want you to make groups of 2. Like this is a recommendation. So actually in the academy, you are more or less 9 people. So look for a partner. We kind of, right now you cannot access the lab, but still you can see each other. Like meetings are allowed until 3rd person. Maybe some of you don't want to see anybody. So you can work remotely still. GitLab is there, and like we have seen clearly that a lot of projects doesn't have to be, you don't have to be presentially there. So the idea is that you choose a partner and you choose a thematic of modification. Let's say you make your nitro pack injection custom machine. We have stayed a few, let's say, spin-offs of the machine. Right now, the machine that we have designed basically is a mini mill. It's a mini CNC that theoretically is able to cut molds and is mainly meant for PCBs. But as you know, like in the lab, we have a lot of extra hardware and things that we can disassemble to modify and make your machines.
One second. You go. Hola.
Yes. So we want you to make the groups on yourself. We don't want to choose for you because maybe some people don't like each other. I don't think that's the case. But also we have seen a lot last year, like all the academy group was really good, like working together in the lab. And when the machine happened, actually they got two big fights, like shouting at each other. So that clear, like sharing the space is not the same that working together. And some people have really strong ideas and they don't want to change their mind. So choose wisely your teammate. As always, like working in teams, you need to have a lot of flexibility and be able to open your ideas and open your mind. And what you initially thought was going to be the final design might change and might not come like that. We want you to make groups of 2, and we actually invite that, of course, all the MD students that they want to join, they can join one of the groups to help in the development of that group, let's say. Okay, do you understand that part? So for example, let's say if Arman and David are making a drawing machine, maybe Magdalena wants to join and also like contribute in that machine. And we will like that Arman and David upset Magdalena. As help. Actually, like always more hands is helpful, more helpful. To give you an idea, maybe we can take a look at the design that we have right now. And after we can go further on the, first I will go on the hardware, like how the machine is, what are the components of the machine. Oscar is going to explain the amazing work he did in the electronic boards. We're going to explain what kind of firmware we initially think that we're going to use. And after that, we're going to show you the possibilities that we have thought that you can develop. That doesn't mean you need to stick to them. Like if you want, you can make your own crazy idea with the machine. For example, right now we haven't stayed to make a small 3D scanner, but maybe you want to do it. So it's completely open for you. So let's go into the machine. Share the screen. Okay, let me go see the chat, sorry. Yeah, actually we are all grown-up people, so we don't want to force you to choose anybody. In case you don't make groups, we will just make a box full of papers and randomly assign them, okay? But I think that you can do it on yourself. So you know that all the information of the machine is already in the repo. Everything, it means everything. So you go to FALA BCM projects. I will copy the link in the chat. Here we have all the projects that we have developed. The documentation of the virtual tools is here. Also the CNC by the sea, the one that you have been using, the inventory app that unluckily this year you couldn't use, the electronic boards that are, for example, the Arduino and the control board of this machine, the one that you're going to produce. So you go to CNC machines. We have the Kraken, a G-code visualizer, and the 6-pack simple portable milling lab. Well, that's also why we state this name, because it's to this called in so many ways. That is our initial, I say 1.2 version, because we didn't make the final one, so we cannot call it 2, but it's not the first version. So actually the machine, as you can see, is really small. So you have it here. Right now we have prototyped the 5mm acrylic version. I think it was Antoine that was asking, okay, but acrylic, does it take vibrations out? Actually, this machine right now has even half of the screws assembled and it's super sturdy and it doesn't vibrate. We have a 3mm version, and this is the platform. The cutting size of machines is usually much smaller than actually the machine size. That's usually a constraint of the machine. So this machine, if I remember correctly, is a 150 50, 150, 200 millimeters high. And the cutting platform is around 100 millimeter, and 80 in the height. Why? Because all the machine is designed from this slider. This is all the mechatronics that produce the movement of the machine. So this slider, and is one of the reasons why this machine is cool, is a really small slider that you can buy, completely assembled, and you see it's super cheap, and has a mini stepper. This mini stepper has a, could be considered, it's not a NEMA, because from NEMA 11, that is this cute size. This is a really small NEMA. They don't call it NEMA. They are custom ones. So this part is a stepper, and this is a reduction gearbox to actually allow to run with much more torque. This goes to a coupler, to a lead screw, and to a nylon. We think that is nylon. They don't specify, but for the color, we think it's HDPE or nylon. A sliding block that goes into two small 3 millimeter steel bars that makes the sliding part. So actually, the total amount of the white part, left to right, is 100 millimeters. Take into account that you will need to put some end stops to notice the end of the career of the movement. You will reduce to 95 millimeter more or less. So the maximum movement of each axis is constrained by this element that is a 100 millimeter movement slider. Ooh. What else we have here? So as you see here, we have a x-axis, y-axis, and the z-axis. Y and z is mounted one together, so actually the y-axis moves directly the other slider because it's self-supporting. It means it can self-support itself. That is a quite nice, good feature because it's a steel plate that is quickly starting, and we don't need to make any reinforcement. What? Let's see. Oh, it's the same. Okay. So all the links of the components are here in the boom list of materials. And for the milling part, we have choose a small, well, it's not that small, it's a RS 555 glass motor. That is a DC motor that more or less has a power consumption of 6 amperes, but what we like is rotate at 20,000 RPM, more or less, at 12 volts. So that is a good value for milling. And the frame initially is thought to be made of acrylic, but could be made of other materials. You can also make out of wood, but wood is really not recommended for machines where you want accuracy. So with this initial design, Oscar has made his electronic custom board that to use the ESP. But this is a 3-axis machine. Could be controlled with a ramps machine or a CNC shield. I want to remind you what is a ramps. A ramps is a control board that all the 3D printers use. That is a Arduino Mega plus basically is a breakout shield where you can connect up to 5 stepper drivers plus 3 power MOSFETs, and you have a lot of pins to output. The CNC shield of Arduino is, let's say, a smaller brother of this one, where you can connect up to 4 stepper drivers but you don't have any, let's say, power MOSFET output. So actually what we did is made a combination of both. Is a CNC shield that works with ESP32 to have more capabilities on the control part, that we can move 3 drivers and 1 MOSFET. On the files I'm gonna send you, because I'm gonna send you the files by BitTransfer, because all the files are in the repo, like the design files, the laser design cutting files, the final design files and the STL parts and the firmware and the components reference, but the 3D files of Rhino are super huge. It's 150 megas, the small one, and the one that contains all the version development is around 600 megas. So those ones I'm going to send you by bit transfer because yes, is it the Zoom windows? Is Zoom? Okay. If you don't see my screen, just tell me, okay? I can go slower because I'm changing the screens and maybe it's because of
No,
that.
they're talking about the same pixel thing that we saw last Thursday.
Yeah, it's just, we are on your left side, no?
Yes.
Yeah, it's Zoom auto censoring itself.
Ah, is yourself.
Yeah, it creates like
Yeah.
a block, a gray block.
Okay. So
That is fine.
initially, we're going to give you, let's say, the basic component part. We are not going to give you, unless you ask for it, like, let's say, the laser cutted pieces. We're going to give you the design, and you're going to fork the project. Let's say you are right now some open source developer, and you find this awesome project online, and you want to contribute and make your own version because you can say you want to make your company and sell it later. I don't know. Because you find a super nice idea to sell this kind of micro machines to schools. I don't know. So we're gonna use the same workflow as any open source project, and you're gonna actually fork this repo and start modifying from it, and take what you want and discard what you don't want. What you will find in this repo, we have the KiCad design files, plus the libraries, plus the ESP libraries and design rules. We have the custom GRBR firmware, and we'll go for it a little bit later. The files for producing the board, the diagram of connections, libraries for the Arduino, for the ESP, the laser cut files for this prototype, and all the boom of list of materials. So this is whatever, all the things you're gonna find. And one of the reasons why we choose the ESP32 is because there is a fork for the original GRBR firmware, that is a control firmware for CNC machines, that is able to use and is compatible with the ESP32. Taking into account the ESP32 is Wi-Fi, I can publish his own pages. The guy that forked it thought it was a really nice idea, and we actually agree, that you can control, you know that you are controlling the Kraken with this web interface. You are doing it through internet, but to publish locally on the same Wi-Fi network that you have, the control of your machine. Why? So you don't need to connect through USB to your machine. So you can connect to your machine and control it and upload files through Wi-Fi. That is a really nice interface. This is the reasons why we choose to use the ESP32. And let's go onto the machine. So right now, the 3 files, we have initially thought this is not the final, let's say, control board, because it looks different, but this is exactly the same size. The dimensions and the holes are exactly in this position. And this is more or less the space that they will take. So let's go a little bit on the machine. I'm opening the chat, so you're going to see another blue window. The doc isn't public. It's going to do it public now. So right now, the machine is made out of acryl, and a good way to fix acryl parts without using glue, that is something that you always want to avoid, is, for example, using this kind of joinery. You know, like it's a 3D model, so I didn't put the nut correctly, but this nut is supposed to be here. That you screw through you have a hole to center the screw of the plate in one direction, and the nut locks the plate compressed into it. Even so, this joinery is already sturdy, but to make it even more sturdier and easier to align the plates, we use a simple joint, like it's not a dog bone, it's called a, ¿cómo se llama? Oh my God, I don't remember now. Los estos.
Castillo.
¿Cómo? Sorry, I didn't took a coffee this morning. So you have the fingers, sorry, the small finger to help centering all the plates together. So you can see that this plate and this plate, to reduce, let's say, future manufacturing times, is exactly the same plate. And the front and the back one, they are slightly different because the machine, let me block this. 1, 2, 3, 4, 5, 6, more or less. Group. So the machine will move the X, and when it moves the X, in order to make the machine smaller, you are moving the X until the limit of the rail. The rail is here. Right now, I just move it a little bit more. Reaches the end, the platform, you want to be able to take it out completely. Because if you don't just make a platform that is exactly the same size of the slider, you're going to have a cutting platform of 2 by 2 centimeters. So if you move the end mill, you're going to see that the end mill is able to reach from here until the other direction, that is more or less here, that is exactly the same. And this is one trick to actually improve your cutting size while keeping a really small machine. For that, actually, the platform, while you are using it, is moving out of the machine. A lot of machines don't use this because they don't need to reduce the footprint, and what they do is just make the frame much bigger. So instead of having the frame constrained to the slider, they have it constrained to actually the working size. So when you move the machine, the platform never gets out. That's another option, and maybe you can make a fork of the machine like this. We just did in this way to keep everything as small as possible and to reduce the total material cost of the machine. So I'm going to take out a few things. For example, you see that the Z, oh, everything is ungrouped in this. Wow. In this, wow. Probably I will forget to select some things, but just to show you. When the Z moves left to right, also in this case, we have a constraint that we have make a hole for ventilation and also to allow the motor to be a little bit out while you move left to right. You see right now, this is colliding, and actually we have another PCB that this was not supposed to be here, that is colliding. Why? Because our initial thought is to, once the machine reaches, all the piece reaches here, we will see where will we attach this slider. We will directly screw the back steel plate to the slider of the other axis. And as this, we can do it with these holes because this slider has a lot of holes. We will maybe mount it a little bit lower, maybe mount it a little bit higher. We will see once we have the machine here. But these are design solutions that we don't worry too much because they are really easy to fix once we have all the parts. We are mounting directly the CNC motor onto the slider, and we have made this. Actually, I remember from molding and casting that we produce this shape to be able to mold it in the future. We have also thought when you have a machine, you always need to think that you will need to have some end stops. In order to take less space, usually the end stop is in this plate, but right now we are working with really small sliders. We don't want to reduce the working size. So actually the slider is in a position that the block is able to move until the end, and when it reaches almost the end, it want to touch the platform and lift it up. That's something important, as we want to be able to change the position of the slider to accommodate, let's say that's what we call machine tuning and machine calibration. We just made a through line slider, so we can actually slide the end stop back and forth to adjust to the final position. So right now, as that's a way of prototyping that in the case you don't know, what you can give is actually leave a few things with probabilities or possibilities on changes without having to modify the firmware. Let's say, the hardware. Let's say you just make the holes If it doesn't work in that position, what happened? You need to cut a new board? No. You make a slider, and like so, it will accommodate all the positions. And in the next generation, you measure where are the screws, and you can just make a hole to be sure that the slider matches that position. What else I can explain of the machine? Oh, this is a really silly thing, but I think this kind of details is something that you will like. This is a milling machine. You know, the SRM produces a lot of dust when you cut and you produce chips. If this is closed, how are you going to clean? This is a really small machine. You are not able to put the vacuum cleaner here, but usually use a brush. Okay, if you use a brush, you take everything in the platform, it falls here. So it's really nice, for example, if you can leave a hole to put all the dust out of the machine without having to actually turn the machine up and down and move it. I'm going to open also the development of the machine because I think it's important that you understand the initial thoughts and how this machine was developed. It's opening Rhino. I think I'm going to cross the other Rhino. Computer is getting a little bit hot. CNC machine final, yeah, exactly. Oh my God, this, why so hot my computer? Don't know. Go on. Okay, the file is huge, 780 megas. That's why it takes so long. One way to reduce cost and usability on the machine is always think that you will need a lot of extra hardware. That in case of open source machines and, for example, the 3D printing community of the RepRap, you have what is called like printable parts. In your case, will be like custom fabricatable parts. Let's say the frame, the mount, the electronics, and everything that you need to buy. They are called vitamins, because it's things that you need to buy yes or yes because you are not able to fabricate. What is vitamin in this case? Vitamin, for example, is the motor, the collet, the rail, and the screws. A good way to design things is always think that you will need to use screws for fixing things. So the first thing you need to think always is, okay, what is the size of the screws? For example, in this case, for the rails, they all use 2mm holes. But for the frame, using 2mm screws diameter is too weak. So actually we have two types of screws in this machine, 3mm for the frame and 2mm to fix electronics, to fix the rails, to fix the end stops. But even so, we have, you know, that screws, usually they are sold in the length of 3mm, 4mm, 5mm, 8mm, 10mm, 12mm, 15mm, 20mm, 25, 30, 35, 40, 42, and 45, and 50 usually. And after you go to 80. So what we did is we tried to choose one screw that could fit all the possibilities. And in this case, if I remember correctly, we are using a 25mm screw, and we try to use it everywhere. So actually, you don't need to buy like 20 types of screws. That increases the complexity of the machine. So try to standardize as many parts as possible. Also helps a lot in the development. Okay, here is the machine. This file is huge because there is a lot of blocks on the machine. So, for example, you see, this is the initial design. The proportion changed a lot, and actually the Z is closed. And Oscar also asked to have this development that is to have an open machine. This is as sturdy, not as sturdy as this one initially, but we'll think that it's sturdy enough. And actually that's nice because simplifies how the machine is made and how many screws you need, then the total cost of material, and it's easy to tweak. So for example, a machine like this is easier to fix and modify if it's the first time you make a machine. So as we initially design, let's say the base frame, these screws are not correctly in place, is we design like what is the shape and the main location of what is the most important part. The most important part location is actually the rails. The first thing you want to design is, okay, how you want to move and how you are going to put the rails in the space. So once you put the rails in the space and you center, you start building on top of them. In this case, we build this frame and we build this frame. And we jump onto the next development. That is, start to try to match, okay, for example, if I put the screw right now is too close from the edge. So maybe the initial design, the plate has to be slightly back. Oh my God, sorry, so slow. Slightly back, so the screw is also back and is away. Oh my God, so dirty this file. It's out of the edge, so actually this piece of acrylic is not too thin and doesn't break. This is the moment when once you have a basic design, you start trying to see possible mistakes and errors to fabrication or that might break your machine. For example, in this step, we also saw that we have this collision. Is you start checking for collisions, but once you have a basic like machine assembly, next step will be actually, okay, I will try to make the shapes. For example, the holder, we have an initial design, but if you go to the latest version, this is like 3 times thicker. Why? Because we measure this. Okay, with this geometry, what technologies we can use for manufacturing? This method of acrylic will imply to have 2 screws here to fix this plate to this little plate, to have another one in this one. So it will increase a lot of complexity to such a small part. So okay, for this piece, it's much better to use a mold or to 3D print the part directly. You can make it sturdy enough. When you have this kind of basic design, okay, we have the screws for fixing. What we can have now to make the assembly and to go into assembly easier. Putting this plate and fixing to 2 screws, there is no constraint that will allow that the plate doesn't slide and move. So embedding some small finger joints will help a lot, not actually on the machine result, but on the assembly of the machine, and this will help for the self-centering of the plates, and that will help that the machine is straight. That is something that happens a lot, that when 2 plates are not straight, the machine is not cutting straight because the whole machine is tilted, and it's something quite important. Once you get to this design, for example, you start fixing things. And this is, for example, the final thoughts on the screws. For example, there is a minor difference in the length of where the nut fits into this piece of acrylic. You want to have it as deep as possible, but not too deep, because not only looks ugly, but you will need longer screws. But if this nut holder is too close to the acrylic, this is going to support a lot of stress. So you want to have a bigger area to dissipate the stress of the screws on the machine. And some minor tweaks, for example, thinking of the Z plate and how you're going to mount it. And once you have more or less a basic frame assembly, you start putting like what is called the vitamins. Okay, maybe here we can fit the electronics, or whether I need to put the end stops. You start previewing where you're going to need to put the end stops. And if you cannot find a position, you will need to go back another version and try to modify the hardware. When you have this one, what I always recommend is, okay, you have this machine. It's a little bit annoying, but make an assembly step by step of the components. Let's say explode it and start joining them together, but do a procedural assembly, just moving the pieces manually, so you know that you are able to match one part inside another one. And that's quite important. For example, when we assemble, I'm going to put a case study. We are assembling the machine like this because we have assembled first this, and this plate. Okay, we have this frame assembled. If I want to put this slider, obviously the logic is to introduce it like this, no? What happened? This slider goes with a small motor. You are not able to match it. So like that, you know that you need to first oh my God. That you need to first mount the machine like this. It means mount 3 plates and the slider, and after put the next plate. So actually it's something that is not that obvious unless you do a procedural assembly. And after we have the, we made everything 2D for fabrication, and what we did is start matching the edges. So actually you optimize the manufacturing time, and when you have one single line to cut both pieces at the same time. So you don't make just have the layouts like, I'm gonna do it actually. I'm just making the pieces 2D. So when you have the pieces out, you will say, okay, I can just put the pieces together properly, and that's it. No, what you want to do is explode this. And as I know, because of the design group first, and explode, sorry, explode. So this line and this line is exactly the same. So what I can do is erase this line, and I can reduce the cutting time a lot, because with just one line you will cut both parts. This is kind of small parts of optimization, and these are different layouts to try to save space. Oscar, you want to go to the PCB? Stop sharing.
Voy a ponerles un poco de la spreadsheet para dejarlo un poco más claro.
Muteas tú, ¿no? Sí. Okay, guys, I'm gonna share my screen. So just before we go to the electronics, just want to show you the Excel sheet here. So anyone that doesn't have access or something, just please request. I'll give you access. In principle, it should be open, but I don't know, these things sometimes don't work. Yeah, hello. So just for you to know, the instructions here are, I think, quite clear, but FA Academy assignment is mandatory, but it's not for MDev students. But since we don't want you to prevent working together, you can do you and mix up as you wish. So please sign up for any group that you want down there and put the name that you want also. That's totally up to you. The thing that you will have to do also is that you need to take the repo. Currently it's in gitlab.com. We do this because we don't want to close access to it in the Fab Cloud. So if you go here, CNC machines and SPML machine, you can make a fork into, if you go into, well, I'm owner of this, so I can't fork it, but you can make a fork of the of the repo and then start collaborating within it. Once you have that fork, you will have to put a name, and that repository link, you can put it in here, in this line, okay? That repository also needs to host a website that will be the documentation for the machine that you also have to make. So with that link, we will be able to see where that page is going and everything. And please specify in your own documentation where that link is as well, so that we can redirect to it. Also the members of the group and the name, the different things you will. Then Fab Academy asked us to have this repo in GitLab Fab Cloud as well. So we will, once you're done, bring it back to Fab Cloud, but we will do it once everything is over. So don't worry for now, just make a fork in gitlab.com, okay? Everything is clear in here, so you shouldn't have any issues. And now, if you don't have any question, I will go to explain a little bit the electronics. So, well, first of all, the electronics are based on this board here. So this is the original development by someone in GitHub. And this is like the version that this user has here, okay? Our version is very similar, but it's of course adapted to the Arduino and making some changes for routing and many things, but in general it's almost the same, let's say. Here you have a lot of resources for documentation regarding the control of the board, the pins, and the special things about, for example, inputs and outputs with ESP32 that I recommend you to have a look at is, for example, in here. And also it has a lot of like references to expressive documentation and many other things, okay? It also gives you information about how to make your own machine definition file, which is a file that will describe how the pinout of the ESP32 have to be mapped to the different inputs and outputs that your machine has. So in principle, we have our own machine, our own firmware already done that Edu compiled a couple of days ago, but you will have to also go here and make your own. Make your own version if you are gonna change based on any other inputs or outputs that you will be willing to put, okay? And finally, just let's go to the actual repository for the electronics. Well, I think it's all pretty clear in the FabLab BCM projects in GitLab. Here you have all the files necessary. It's a KiCad project. In principle, you should be able to download all these things and it should be just plug and play with all the internal references. If not, if there is any problem, please open an issue in this repo so that we can fix it. And that at least we have the record that there was a problem and now it's fixed. But here it is. So if I open KiCad, this version, let me see if there's anything in the chat. Okay, so this version is based on the Arduino, but as a smaller version of the Arduino than the one that you have. And this is this one here. So it's a little bit smaller with micro USB. Giuseppe made a version with the FTDI chip, the same that you use for programming some boards, included into the board. And in comparison to the other one, this is the one that you have that you did with the FTDI header, and this is the one that you will be using. We also order some of these to manufacture, but this is all totally fathable.
That is the difference when Edu designs a PCB and when Oscar designs a PCB.
Well, whatever. But here, so the idea is that this PCB will be a header on top of the CNC controller, and the same way as the original designer did this with an old MCU. Okay, so this will be on top of the CNC shield, and this is what you see here. This is this component, and you will have quite a bit of inputs and outputs. You will have inputs regarding end stop like X limit, Y limit, Z, positive and negative, and the probe. And you will also have some digital inputs that we like are generic for CNCs, like hold, if there's a door, start, GRDL, reset, etc. That are internal reference for the firmware, but that you can modify as you wish.
What is the probe?
The probe is the same thing for if you want to do the set, like set probing. Is at the end that is just a switch that will hit on the bed, on the surface of the bed, and will close the switch whenever it touches. So that's basically the input for that. Okay. So it would be, Ed is saying that in like, as you, well, I don't know, you didn't get to know the shopbot, but in the other machine that we had here, the CNC machine, basically you have a clamp, a metal clamp that makes a short basically on one of the pins, and then you detect that there's that you are on top of the surface, and that's how the machine makes knows that you've done the zero of the machine, or the bed leveling. So. Then regarding well, that's all inputs. If you see in the schematic, is all very like intentionally tidy for you to have everything clear. There is outputs with two modes for outputs besides the stepper motor, the controllers for the stepper motor, which are a control for a spindle, external spindle based on a PWM. That will be a 5 volts output, and a spindle enable in case you, for example, have an external relay or a controller that needs like an input for enabling the controller itself, or a MOSFET. You have that in 5 volts and in 3 volts. And also you have a regulated PWM also outputting from a MOSFET. So you could control motors up to 12 volts DC, or smaller things like 5 volt DCs with PWM, or you could put an external DC board for control.
Yeah. These outputs are digital signals. It means they are not power signals, like you are not big current. So this one can activate a relay, a MOSFET, other things. But if you connect a motor directly to them, the motor will not work, or it will burn down the ESP. Mm-hmm. So in case you want to connect a power driver, a power train to these pins, you will need to put something between, like a small power plant. That could be in the order a relay, a solid state relay, or a small MOSFET board. Mm-hmm. This is for activating digital pins out.
Yeah. So those are the spindle, the PWM ones, but also here you see the MOSFET. This is actually a regulated, well, a PWM MOSFET output that you could control a motor between these two pins in another header in here, okay? And it's already protected with a flyback diode and everything, so that you don't damage the board. The only thing is that we don't have enough control pins, so you will have only one PWM that it will be translated either into 5 volts output PWM, 3 volts output PWM with a level shifter, changing just voltage level, or the MOSFET output. But they are all the same PWM, only in different voltage levels, okay? Is that clear? And here you have a small jumper that will allow you to select which ones you want as an output, okay? So that you don't have all of them at the same time. Then you also have an SD card in case you want to, yeah.
Oscar, you use one PWM output and you have like a switch that changes the...
No, this is, it's called a jumper. Basically, well, actually, espera. So if you go, so if you go here in this picture, you can see it very clear. So you see these yellow things in here?
Yes.
So basically, this is just a header pin, like these ones, more or less.
Uh-huh.
Basically, you are making a short between them with an external, let's say, what we call bridge. And these are removable so that you can put them or not based on some configurations. And that's what we are doing in here. So you are outputting either through the MOSFET or either, well, you are outputting always through the PWM, but if you want to select the MOSFET, you just put the bridge in there and don't output through the 5 volts PWM.
Okay.
Basically a way to select how to route your circuit with external hardware, let's say. Then, what else do we have here? So apart from the SD card that actually, I don't know how much we will use.
It's needed for
what?
For storing the files.
Okay, so when you upload the files, they will be in here, I assume?
Yes, you can make a live stream of the file from your computer, or if you want to run it standalone, the same as you do, for example, with a 3D printer, that you load the code and it's there and self-executes, you need to use the SD card. Because the ESP has almost all the space use of the memory on storing the HTML interface and the control firmware.
Okay, then with respect to power, you have a barrel jack connector, like this one is the same that the Arduino Uno has. And we have are these little guys that can support up to, well, I don't know this buck converter, but in principle, we will be inputting 12 volts DC. And this buck converter is basically a regulator, a step down regulator that bring that down to 5 volts in a stable source that we will use then to power our board. There's a nice red LED so that you have some indication that the board is on. And also there's a small
28 volts.
28?
Sí, de máximo de 4, 28 y 3 amperios.
Okay, so normally we will be working at 12, but this thing accepts up to 28 volts as an input. Here, a very important thing is that how this is wired, and you should be careful with this because if you use an external power supply that is not the one that we will provide you, I think, you have to be very careful how the polarity of this barrel jack input is, because sometimes they can switch, so they are switched. So you have, in this case, the positive is inside and the outer part is negative. And just so you see, if you go to Adafruit barrel, no, power supply DC, jack and supply. Okay. Chat here. You have some indications about this. This is talking about the Arduino Uno, which is exactly the same barrel jack connector as the one we have. And here, they explain a little bit how the polarity of this works. And you see that this little indication in here explains how that is wired internally into the jack. So the inner part is, we have exactly the same as this one, is exactly the same as the Arduino Uno. So the positive is inside and the negative is the outer shield, okay? If you revert this, there is a diode inside that will prevent like reverse polarity connection, but basically your board won't work. But we thought about that, and that's what the purpose of the diode is in here, okay? Very likely you will end up probably burning this thing, but not anything else.
It burns, I know.
This thing?
I know by experience it burns. I have used this one.
And then with respect to power as well, one very important thing is that the Arduino is not powered by default from the bottom part. You can power the Arduino with the USB, micro USB connector in here, but you can also not have that connected and power it from the bottom shield, let's say, and there's a slide switch that will allow to select if the power from the shield down is going up to the Arduino or not. And there is also, let's say, an LED indicating that there is power going up to the Arduino, so that you remember that you shouldn't, or you could have the USB connected as well. But in case there is a problem with like a voltage mismatch or something, you could probably burn the Arduino, or at least the FTDI chip or something like that. Okay. Then, as you know, the Arduino talks at 3.3. All the logic all the outputs are 3.3. So we have a level shifter. A level shifter is nothing else than a voltage level converter that will switch from 3.3 to 5 volts. And we use that for the spindle PWM. So we will output a PWM in 3.3 volts from the Arduino and go up to 5 volts. Both of these outputs are available for you. And of course, the spindle enable that is also used to trigger the level shifter. Exactly. So in this design, there is 2 options for that. And I will explain this with the board itself. So here is the level shifter area. And there are 2 possibilities for doing this. One of them is with an external shield that you just plug in onto the CNC shield, let's say. This one, we bought it in AliExpress or something like that, and it's basically a custom circuit that already contains the necessary chip. But so that our design is flexible and we don't have to rely on that shield in case one day they stop producing it, we also included the necessary footprints for making that work without that shield and having a space for the little chip that you have in here. So that's what you see. That's why there are 2 areas. And one of them is the level shifter with the PCB, and the other one is a level shifter optional for no external PCB. So in case that you want to put the electronics with that. And finally, the most important part of the whole thing are the stepper mod, the controllers, which are classical Pololu breakout boards, and like so are these ones. Here the Pololu documentation is really, really good. So you can have a look at them in the documentation about how they work. And ours are red and not green, but the rest is exactly the same. So here you have specs and everything. There is one thing that you have to take into account is that if you see in the wiring here, the outputs that you will have are directly connected to the, let's say, the header connector that we have in there. And there is also a configuration for micro stepping. Okay. So, and these things are generally quite standard. So you will, if you want to use another one, like a DVF, this is also like a compatible stepper driver, and probably many other stepper drivers will be also available for you to use. Here there are 3 pins that are in here are the micro stepping options that also if you pull them up to 3.3 with these bridges that we were talking about, you will activate them. If they are flying or not connected, then there is not micro stepping options. And if you want to have more information about this, if you visit in here, they will explain the different micro stepping resolutions that you have.
Micro stepping is actually, you know, that usually we consider the standard for this kind of technologies. The steppers move degrees. And depends on the stepper, usually the angle of movement is 1.8 degrees. So one step is 1.8 degrees. That is what is called a full step. These drivers, they can do by software, or they can enable by software hardware capabilities. You remember from a stepper and driver inside. ¿Sí? So the resolution of the steppers is meant by these lines, and when you rotate 1.8 degrees, it's considered a full step. This means this coil is making force on this coil. They have reverse polarity, so they lock the movement. What we call microstepping is actually have them change really fast. So actually, you don't move anymore 1.8 degrees, but 1/4 step will be you are moving 0.9. That produces that basically the motor is doing this, but it's doing at super fast speed. So actually you feel it that is locked in place. And that is called 1:4 resolution. You have 1:8, that 0.45, 1:16, you reduce it to 0.22, and 1:32 that you reduce to 0.1 degrees. So actually increasing the resolution of the microstepping, you have more control and you can make smaller movements. But also you have other constraints that in Pollulo webpage, if you are curious, you reduce a little bit the torque of the motor, etc. So microstepping is used when you want to increase the resolution and accuracy of your machine, but you lose a little bit of capabilities. So depends on the stepper driver that you are using. For example, this one that is purple, that is called the DVR8826. This one can only go up to 1/16 microstepping, but the one that we are using can go to 1/32. So depends on the driver that you use. It has more resolution or less resolution. For example, the newer generation, the one that came out this year, I think they can do microstepping of 128. That is huge. And
so basically
now what is the resolution that we have, not in the angle but in the movement? So one step in movement, if it's a full step, how many millimeters does it move?
That will depend on the lead screw of that you have connected your stepper, because you are translating a rotational movement into a lead screw, and it's not the same having let's say the lead almost planar that having really tilted. Actually, the one that we have right now, you need to move, I think, 56 steps to move 1 millimeter. So it's quite accurate. And actually the drivers that this slider that we bought are meant to control DVD room laser readers. So they are really quite accurate. So we will not, ideally we will not need microstepping at all, because it's already super microstepped motor. But if you want to increase the resolution even more, you could be able to do it.
And
thank you.
We don't need, I don't know if Daniel, that was the question, but these pins are inside the breakout board on the stepper driver, but we don't have to do anything else, just bringing them up to 3.3. It's an internal configuration that the stepper driver works like that internally, but we don't waste a pin on the Arduino to do that. We just put a bridge in here. And actually, probably this was not necessary, but since when you try to design something, also, if you want to not have to work again in the future, you just make it generic, and maybe this board is not used anymore for this machine, but can be used for anything else.
Actually, it could be used for the Kraken. That would be really good.
Exactly. So, and that way you don't have to, let's say, redesign the board or make any modifications. This is already adapted for that. That's why there are extra things in here that will more or less try to help that, try to help us in the future. One of the things that, if you are willing to work on it, is there would be a need for another stepper driver if you wanted to make this as a 3D printer, and you will have a little hard time if you want to keep the same amount of pins in here with the Arduino. But I encourage you to make either an external driver controller or reduce the number of pins that you use for inputs or outputs, and then put another stepper driver controller if you want to. At this very moment, we are limited to 3.
Eso no lo va a entender. Hay un ejemplo, si pones stepper driver expansion board 3D printer, hay un ejemplo de este tipo de placas que se ven. That actually that is common in 3D printing world. If you want to use, for example, dual core extrusion, most of the expansion. So actually, a lot of machines boards doesn't accept more stepper drivers. So they actually sell this kind of small PCBs that you guys just need to connect to 3 digital pins, and they will enable to have another external driver out of the board without having to modify the main board. Because to control these small guys, these small stepper drivers, you can reduce it to only 2 pins and giving VCC and ground. That's enough to just control them.
And actually, if you see here, this is a very beautiful solution as well for the micro-stepping solution. These are like these deep switches that you use, I don't know, probably people that have been playing with lights or machines that are controlled with addresses have seen this. But it's basically the same thing. Is what we do with that bridge. So I also encourage you, if you want to design one of these and then put it in the repository.
Expansion board.
That will be quite amazing, actually. What else? That here, there. So let's have a look at the actual board. So
easy.
This is how it looks. It has a lot of things going on, but it's not that complicated. It is a 2-layer board. Here you have the Arduino. Here you have the SD card that is on the, let's say, on the other side of the Arduino. And actually, let's have a look at it in 3D. Exactly. So.
Sorry, so what you're showing right now, it's the board, and the Arduino goes like a shield above the board?
Exactly. So that's exactly that. So the Arduino, let's say, would go on top of the board as a, let's say, like the shield in this case is bigger than the controller. So the controller is the shield on the shield somehow. It's a little bit weird, but is how it is. So here will be the Arduino with like headers, like I don't know if you see my camera. Yeah. So basically, the Arduino will go on top of that, like that. Here you have the stepper drivers, let's say sockets. Here you have a strip of inputs. Here you have a strip of inputs and a strip of outputs. The SD card will be on the other side. So I don't have my mouse and this is very difficult. This is where the SD card socket will go. And the barrel jack connector for the power, the MOSFET, the level shifter, the power regulator, of course, all the extra components that you need for making this work.
And are all those inputs and outputs already in use, or are then
free? They're free.
They're free, okay.
Except for the limit switches, that of course we need them, like one for the X, Y, and Z. For example, the ones that I remember that are free right now is flood, mist, probe, extra limit on the Z, start, door, and hold. For example, what is hold, door, and start? Like this PCB is mainly designed for CNC. In machines like this, you remember that the SRM, when you open the door, the machine stops. That actually will be door. It's a safety mechanism, so usually it's like to put a switch or a magnetic sensor that when you open the door, the machine pauses.
Okay, but they can only be used for those functions, or is there any?
You can use them for other functions because it's the same. These functions will be the same custom G-code commands. For example, right now, a start will be with a G4 that is a pause button or dwell button. But if you send the command whenever you want that G4, instead of pausing, you can enable whatever thing. Let's say servo, or I don't know.
Yeah, I was gonna ask you that if, for example, I wanted to add a P1, P2 command, G-code command of a servo, where should I install it? In any output, or are there any specific outputs for that?
And the ideal is that you look for a PWM output for servo because they are more accurate.
So what I would recommend that you do is that you go here and find one that suits you for the GPIOs. In principle, anything that is in this list, you could use it. And then go to the schematic of the Arduino. Here you have the GPIO names, and here you have where they go. And all these names are, of course, written in the board itself, in the, let's say, the silk, so that you can find them.
And
map them as you wish.
And in the firmware, está el repo por aquí abierto. El nuestro. And in the firmware that is already here, this is, wait, we need to move the screen. Yes, if you go to GRBR ESP, this is all the files of the machine, but no, where you define the pins is actually in machines. We already make the selection is SPML. Yeah, this is all the configurations of the pins based on like Oscar PCB. But for example, you can swap, for example, mist and flood, or I don't know.
Exactly. Exactly. Huh? How? Yeah, maybe. Yeah. So maybe, well, now it's time. Well, do you have any question, guys?
So when you made that board, you order this shield, you order it, and it's going to be with that text or something like that.
Yeah. So when you order this, or when you finish this thing, here in KiCad, you have all the ones that contain this text is front and back silk, and basically you can arrange them as you wish. I try to be the most ordered and tidy possible so that you can see each of the pins and how to connect and what are the values of the resistors, etc., etc. And then when you go here to file plot, plot format as a Gerber, Gerber is the most generic export file type for fabrication. Then you use here, you select here, and then you export this. When you export a layer that has front and back silk, the manufacturer will already understand that that contains something that they have to put as a serigraphy, like a vinyl on top somehow, that will like make your life easier, so that when you solder and everything. And also, of course, we put here our name and version and licenses and stuff. Yep. And if you have a look in here, then it's like how it will end up looking. Also, there are these three holes for supporting the board onto the machine. There are only three because I couldn't fit four. But
Three is enough.
Three is enough, yeah. And here, just to clarify, these are, for example, sorry, this is, for example, the switch that I was talking about for sending the voltage up to the Arduino, let's say, and here is the power.
Oscar, which parts of that it's the license? The CERN OHL B1.2?
Yeah. So CERN open hardware license B1.2, yeah, which is basically fully open, share alike, like it's not permissive, so it's like you have to share it with the same. You can do it as whatever you want, but you always have to attribute that. The same way as we attributed the guy that made the other one. That is not we didn't make a for, but we brought a lot of inspiration from his design. So that's why he's mentioned everywhere.
So we were saying that share alike, it's that if you are gonna modify it, you still have to share it.
No, you have to share through the same license.
Exactly. So that's actually like, I don't know, it's very confusing if you don't haven't fought in that world yet, but it's let's say on the, let's say, copyleft end, so licenses that don't have that don't hold copyrights or don't close things, there are two main distinctions. There are the permissive ones, which are actually less permissive, and the non-permissive and the fully copyleft licenses. The copyleft licenses mean that when you deploy something, people have to do it. If they copy it, they have to release it with the same type of license as the one that you gave. But the permissive actually is contrary to what you would think, is not the same way. So someone could close afterwards the design that they copied from you. And it's like, some people say that you have like permissive licenses give you more liberty in general, because you can copy, but then it even gives you the liberty for you to take the liberty out of others, which I don't think it's liberty, is just closing things, you know. But enough talk for that. Let's go have a look at some configurations. Here we made, well, oops.
I will share the picture also in the chat.
Can I ask something?
Of course.
Before we go further. Neil yesterday showed this board that it was controlling with the like a network communication. So each motor had its own shield beside and was sending data through one board, like a satellite. Could you kind of a bit elaborate on that? Because I didn't understand it fully.
Yeah.
I can send the link.
Yeah, that is the clear example. Is if you go to the documentation MTM machines of Nadia Peak, and actually we have a few boards of those ones in the lab. And actually before, until 2 years ago, it was mandatory to do the assignment with those boards, but it was too complicated, and the students had a lot of difficulties to control it. So basically, a networked machine. Let's say a traditional machine, let's start with a traditional one. You have a control board with a microcontroller that sends the signals to the stepper drivers, and the stepper drivers moves X amount. And the matching of kinematics between, for example, X and Y is based on the timing that the microcontroller estimates for mixing both movements. A networked control system behaves completely different and has a lot of benefits. For example, it means each stepper has a small PCB, a small board that has its own controller, his own stepper driver, and basically you have an address that you are calling. Let's say it's a network of motors. That's good because you can expand the system really easily. For example, you can just connect another motor with his own stepper board and call it with the same address that another access that you already have. So actually both systems will work at the same time because you have the same address. Let's say you can easily expand a machine from only having one motor for X to have like 5 motors in X if you want. So it's a system that is really easy to expand and is really multi-configurable. The bad point is, yes, you are calling an address to a motor and you are stating that it needs to move, but there is no one managing the general movement. Each board manages his own personal movement, but there is nobody controlling what is the coordination between different axes. Because sometimes an X, if you are moving in the diagonal, you need to move at the same speed, X and Y. But let's say you are not moving in diagonal, you are moving slightly tilted at 20 degrees, making a 20 degrees line. The speed in one direction is different than the speed in the other direction. And sometimes they need to accelerate at different rates. So they actually made a line at 20 degrees. So actually how you coordinate those systems is not done by any microcontroller. It's done on the computer, but having estimation on the time it will take for each one of the boards to move. And so those systems, you need to have bidirectional communication. As a standard unified control system, you just have it's unidirectional, you just send the commands because they are already estimated. Meanwhile, in these systems, you need to have bidirectional. You need to send the command and be calling at which position you are in. So actually you can stop or break down one of the motors so it keeps the real position that it needs to be. It's not a closed loop system, but the integrative part on the estimation of the positions and speeds and acceleration is much more complicated. And actually, for example, just look for the MTM machines of Nadia Peak. I will write in the chat. I don't know where is the chat. I will look, type it later. Is that board? We have actually like 6 board of those ones. Yeah, that's right, exactly, that's link. And I don't know anybody that has reached to have more than 3 axes, because the kinematic control bit to estimate the 3 axes at the same time is really complex. But actually with 2 axes, it's much simpler. And actually, I think if you're interested, you look on the project and we have here the Nadia Peak boards and you program it in Python. So that could be another option for this machine. If you want to use these control boards, you are also welcome to use them.
So in this case, to be clear, the solution about coordination between X and Y and Z is that the SP32 knows it all and just sends the signal to each stepper driver or say move, and that's it.
Yeah, move this amount of steps, yes. And knows the time it takes for them to move. But on a multi-network system, you cannot just tell move. You need to self-adapt in live. So actually, compared to traditional unicontrol system, let's say, you are not controlling them in live. You just send some predefined instructions. So on the other hand, the multi-network control is good because it's mostly designed to be live control, like with real feedback. Say that.
Well, here we made a small summary of some configurations we could think about. It doesn't mean that you have to stick to any of this. It's just some ideas. Some of them, especially we were thinking about, for example, David, you could make an infinite drawing machine with like an infinite belt where you put paper on one side, a drawing machine, and then you draw a comic like a strip on the other.
Toilet paper roll.
Toilet paper, for example. But anyway, jokes aside, this is just to show you the different possibilities that we could think about and the things that you would need extra for each of them. So here is the basic configuration. You already know this. You have.
Can you zoom, please?
Basic better.
We have state different options with different levels of difficulty and also with different constraints. Some of them needs a lot of work in the hardware, like how you put the motors and things in place, and other ones they need a lot of work in software, and other ones in the how you make the G codes. So we have state different options.
So for example here, no, the injection machine. So this would be like an injection pump with one of these guys that you can also control. This is a 12 motor, 12 volts DC pump that has up to 2.2 bars in pressure and 0.8 of vacuum. We have all the materials that you could need for making this as an injection machine for bioplastics or whatever else you want, like
Nutella or chocolate, or like
anything.
Based 3D printer, basically.
Exactly.
With low pressure.
And here you wouldn't need to modify anything with respect to the electronics or anything because you already have an output as a PWM for controlling this guy. You would have to focus a lot on the hardware modification to make the support for the syringe, to
maybe embed us.
Exactly, to open and close the thing that you have enough inputs, output for that. What else? A laser pointer one that you can also control already off the shelf. And the only thing regarding hardware that you will need is the laser pointer that we have. Is that or no?
Yes, the ideal is make a laser cutter, a small laser cutter, but we don't have powerful lasers, but that's the idea. So for example, you can make your own, as the hardware part in this one is quite straightforward. What you can do is, for example, implement a small processing app that you input an image, automatically vectorize it, and connects to the machine. And let's say it's a nice interface that automatizes all the G-code part to draw to cut with a laser cut.
There are references for that in other GS for Fun Academy. Like final projects from people doing this type of thing. So maybe also if you want, you can check on the docs for Fun Academy for some other people doing this type of things, like laser routers and these things.
I will recommend strongly that you look until 2016 of machines. Usually there is only one machine per lab. So take a overall look on what everybody has done, because we have seen massage machines, like tattoo machines, pizza cutter machines, and that will open up like the scope of what you can do.
What else? Light painting machine with an LED strip or a RGB LED for drawing, like making these in the darkness drawing when you control the position of the LED and the intensity. and then you make a like a long exposure photo or yeah, for that, and you make like a live painting machine. The only thing here is that if you want to use NeoPixels, Edu, you were saying that you cannot use them with GRBL, you said?
No, GRBL doesn't support NeoPixel, so actually you will need to may take Marlin that is from 3D printers and modify to match this PCB, because Marlin supports NeoPixels, but GRBL not. Or make your own software to control it based on positions.
Or you could just put one small RGB LED that you can control with three of the free inputs that you or outputs that you have. So just so you know, that the person that is doing this is that guy. This is the one guy that is ruining your class.
Watching YouTube videos.
Searching for reference.
Yeah.
Nice.
Okay. The most complicated options that is, because I know Bruno asked for it, or I think it was Roger, is make it a small 3D printer. That implies a lot of work in a lot of all the fields. You need to port Marlin to this machine. You will need to make the connections to the heating cartridge. That's easy because we have the power MOSFET. You will need to make a small PCB for the temperature sensor with a voltage divider to get proper readings. And you will need to make an external driver board to be able to run the motor of the extruder. That is you want to have full control as a normal 3D printer. Another option will be to make a small control PCB that controls the heat, the temperature, and the motor, and you only have extruder on, extruder off. That actually is what we do with robots. And you adapt the speed just with the GRBL of the machine. And what you do is you switch on, you connect both boards, like sending a spindle on that will send the signal to the other board, and that will manage all the temperature, motor movements, and heating part. What else? A mini lathe.
This one, I think I would love to see this one. Like really, I would love you forever. So the idea is that you know what a lathe is, right?
No, I don't.
No.
No.
A lathe is a café con leche, isn't it?
That's a latte.
Plop.
Actually, this project has already been done in the academy per se, of course, not with this machine. And actually, they made some custom pipe cutters, and it worked really, really well. And it's quite amazing machine that is really nice to see it working.
Is
Okay.
it like a Dremel or something?
Imagine a 3-axis CNC, but that you have a rotational tool that can flip your part.
So first option, an easy one is something like this, okay? Basically you have, this is making, this is a machine used to make like rotation, like revolutionally generated pieces, like that you can make out of turning something symmetric with respect to this diameter, let's say. So basically this is that this support is rotating. In this case, you would make it rotate by a motor. And then there is a static tool that, depending on the shape of the tool and the material and everything, will take more or less material and whatever. But that basically is moving in this axis and in the axis coming closer to the, let's say, the axis of rotational axis of the part. And by doing that, if you control that movement, you can make these type of shapes like, I don't know, the legs for your table, or even this other, the chisel, I think it's called.
Yes.
This will be done also by a lathe. Basically, it's making for rotational parts. And the idea is that you could convert this machine into one of the into something like this. And there are various formats for how you hold your part and how you move the let's say this the bit that is going to be taking material out. So for that, you have different options. You could have the option like this one, in which you have 2 points that are aligned with each other, and by putting pressure between them, then the piece is held in place. But you can also have this other type of option.
For access,
okay. Aquí está, ¿no? Esto sí. So if you have a look in here, you see this clamp mechanism, which is basically these parts. Let me look for a video.
There's like fingers that they close and open based on a small gear system. And these, actually, they are designs 3D printed already that you can use, because this usually is slightly complex on the way it grabs.
Like,
no, es que no va a salir así. Pon 4 axes, en los 4 axes siempre sale. Rotational axe, 4 axis rotational axe. Axis. CNC. Pon siempre suele salir. Aquí está. Makers Media Network.
So you see in here, these parts are holding the let's say the brute material, and these guys are let's say clamped into the material by just pressure, and you tighten the map mechanically, and then the whole thing rotates. Then there's other this part is optional and depends on how long your, let's say, the piece that you're manufacturing is.
The cantilever you have.
It's basically, as you know, it's going to be rotating, and there will be probably some vibrations, and this thing, if it's rotating too fast, it might generate vibration and then fuck up your part or even break it. So you can give some external support on the other side. It's very important, of course, that the center of this tip in here is aligned with the rotational axis. So that is something that you have to take care of. And as a final solution, instead of doing this, you could also imagine a system like this one, in which instead of having those fingers, let's say, you have, let's see if there's a point, exactly. So you see in here that we have left this base in the very, well, not we, these guys or whomever, they left this part in here, and there's like a plate that they put some bolts into the piece so that they hold them in place. And that is also a very common solution. The only problem here is that you have to be careful not to touch those parts, and you sacrifice some material that it will be used for your, let's say, base, and then you cut it off if you don't want it in there. But you basically use, let's say, this part as for the fitting, and you don't have anything that needs to be clamping because probably the part is too big.
For example, this is you see, it's a end mill cutting at high speed, but we have a 4 rotational axis that allows to make really 3-dimensional parts by mixing both movements. And how you make the G-codes for it, don't worry too much, but because RhinoCam produces also 4-axis milling with rotation.
So that's what we should be doing.
You could make Michelangelo's stuff.
Also, this option could be enabled in the laser engraver tool because actually this is something usually used for engraving bottles in the laser. And it's called the third rotational axis for the laser cut, because the laser cut has already only 2 axes.
So having said that, you could modify the milling machine either by, I'm gonna close this video. Either by just keep modifying the DC motor that you will have as a vertical axis and adapting this part so that it can hold your part. So basically the lathe would be a vertical one, or you could modify the whole configuration and do it as more traditional one, in which you have the horizontal axis and then the tool is going up and down. In this case, either that tool could be a rotational one, like a mill bit that you also control, like in the last example that we saw. And for that, in this horizontal one, you will need a stepper motor, or you could have a DC motor in here and then just make parts like this one, in which you wouldn't have that 4 axis. And this machine, the configuration with just the DC motor, you could do already off the shelf. And the other one too, no?
Just need to make the small stepper.
Yeah, exactly. So you would need to put an external stepper driver for driving this in case that you want. And this wouldn't need to be like a super big stepper. It could be like an MI11, you said?
Yes, I think MI11 would work well.
Exactly. And the important part here is how you hold the piece in place, how you align the axes, of course, and then the G-code generation that apparently is very easy with Rhino.
Other options that we have not stated in this diagram could be a small laser scanner that you have seen through all the years of the academy. There's always one like 3D scanner with a laser and a webcam, for example, or like the ESP cam. Other options could be to make a, how it's called, drag knife cutter. Can you look in it in YouTube? That is something that is an easy way to transform CNCs into material cutters with knife. Well, it's basically as an end effector that adapts to usually the CNC motors that has a knife, and you cut usually for cardboard, like vinyl, or materials that could not be cut in the laser cut, also like leather. So for example, you see basically is leaving the motor without actually to be on, and rotating with the blade as long as you cut. For example, the platform CNC making a drag knife is a really nice example on how you design one of these ones. It's all the step-by-step on how to make one in aluminum.
Okay.
It's a quite common modification for CNCs. Okay. Do you have any question, guys? Apart from the chat?
I have one.
No
I just want
question?
to ask. I just want to ask.
So let's have a break and try to make groups. Okay, meanwhile the break.
Yeah,
I have a question also. Oh, yeah.
Both think like Steve, Stallman, Richie.
Go for it, Alman.
Yeah, okay. I just want to ask that, do you think, I guess they can't hear me. Can you hear me?
We don't hear, wait.
I hear Arman.
Can you hear me?
Yeah, sorry, it was our side.
Oh, okay, okay. I just want to ask, do you think the pick and place machine, it would be hard for this assignment?
No, actually, it's really similar to the paste extrusion. This pump can make pressure and vacuum. The vacuum amount I can make is small, but usually what you do is use a small needle or really small syringe system, and you use the vacuum from the pump to release.
Okay.
Actually, you will need one of these pumps and a small air valve solenoid to release the air and wait, like to differentiate which circuit you are taking the air from. But the pick and place will be really nice, actually.
Okay, thank you.
And how do we have to deal with the software part? In all the example, you always talk about the hardware, how to control stuff, but how do we, I don't know, how do we understand and interpret the result we get?
Antoine, you are talking about producing the code or the firmware that controls the machine?
Everything, I guess.
Okay, depends on the options, because some of you, they don't want to mess up with the software. You don't need, if you don't want, you don't need. Like the machine itself has already the firmware working, and you can just load G codes, and depends on what kind of G code commands, it will produce some things in some outputs or some inputs. In case of the how you produce G code, it's a standard G code, the same as the Kraken. And
so in Spanish, there's one expression called echarse a los toros. It's basically something like from bullfighting. It's basically that we will put you now in front of the bull, and you will have to figure it out, more or less. We will.
Okay.
We're not even in front of the ball. We've been showing the ball digitally.
Exactly. So something like this. Not that I support this thing, but just
expressions.
Spanish expressions, yeah. So basically, we are echando you to the toros.
Gracias.
Like really depends. Each year, I want to be the good guy now. So you can just choose and use the software as it is, or modify and use your custom firmware or use your custom G code. Like we try to the electronic board, that is the thing that you will less modify from these kind of things, is compatible with almost everything, or as much as possible.
Okay, thanks.
Okay. Let's have a 10-minute break. It's okay?
What up?
Doesn't mute.
No acabo de unmute. Hello?
Hey there.
Okay, guys, so let's have a look at the spreadsheet. We see, oh, the OK group from Antoine and Benjamin with shifted surnames. Awesome group. We have one that I'm gonna delete. I don't want those guys there. Okay, so 2 groups only. How many are you guys? A lot. So please start organizing if you need help or anything from us. Actually, I'm gonna put also the picture of the ideas in here.
Maybe if we just enter random people's name and then they can just rearrange them or create the groups for now. Arman, I'm going to choose who you're with.
You do you guys.
In case of Antoine and Benjamin, do you have an idea of what kind of thing you want to do?
No, we were going to meet today and have a chat about what could be done.
David and tu?
The drawing with lights. I like the idea, and I need to work with the LIDs and something like that. So we are going to try to make that and maybe use some mirrors or something like that.
Okay, that's nice. For example, what you can do is, as your machine doesn't need to be that sturdy, you can make a super minimal frame that just supports the sliders. So more like a pole that moves the air, and you can take bigger pictures from different angles.
But first, I think we need to study all the framework and try to understand it so we know what we have to modify it.
Arman and Daniel, another group.
Okay.
Arman, what do you want to do? Daniel cannot speak, so you can say in the chat.
No, I put Arman in.
I don't know.
I literally just put the names so people are forced to move their names to whoever they want to be with. Otherwise, they're just probably not going to put them. So
Honestly, I don't care so much. So anyone who wants to be my teammates.
And the rest of other like MDev students, again, if you want to jump in with any other group, just go and like talk with the people in the group and say, hey, can I be with you? Can I be your friend? And then you can, you can collaborate. And as you know, you don't have the same requirement as FA Academy, but we encourage you to do it. And will be very nice.
And they're smarter than us, so we need them.
Especially smarter than you.
Yeah. They're doing a master. They're doing just FA Academy.
There is other option that we talk about. I don't know if you know what is alu bond.
Someone is mute. Someone is mute. Someone is mute.
Sorry, can you hear well?
You have some echo.
Now we can hear you.
No. So the alu bond panel, what you can do is just cut one of the layers of aluminum on the foam with a V-cut end mill and just bend it. So what you can do is make the whole machine design to be folded and assembled. You will still, let's say, have a CNC, so you need to think about the firmware or like the control or anything, but what you will work is completely on the casing, on the hardware frame. And you can optimize to be like a folding origami to make your own machine. Let's say, and you can flat pack it and ship it without any screws, just as a IKEA folding furniture. That could be another like spin-off of the project. And actually, I would love to do that too, that you can also do this, because it would look really nice to have an aluminum small mini machine without any kind of screws. So many feedbacks. My mask. So I don't know if today is Thursday. Tomorrow, if you want, tomorrow we don't have a session, but we can do is connect, for example, at 12, and you can discuss tomorrow afternoon, and we can check what is your proposals and what you can start thinking, and maybe guide you a little bit on how you can approach your design. Are you okay with it?
Do we have the time between 3 and 5? Maybe we can use it.
Okay, we can use the time between 3 and 5. Let me check the calendar. Do we have it, Santi, no?
What? Sorry?
Tomorrow between 3 and 5, like the open session.
Yeah, it should be there.
Yes, open live instructor on structure tutoring. Yes, we can have it tomorrow at 3 to 5. We can check a little bit your initial thoughts and how is going to be your approach. Like, of course, you need to study a lot today and tomorrow. Like, there's a lot of documents that you need to go through.
And you're going to send us the WeTransfer of the Rhino files.
It's on the spreadsheet.
It's on the spreadsheet. Okay.
Yes, is the after SPML repo 3D machine design files. This is the WeTransfer download link. Yes. Vale. Yes. So Oscar wants that we share that when you luckily finish all your machines, they are working nicely. We will fork back, or you can merge your contributions as a spin-offs of this machine, so we can have everything in just one repo, and some people can start building on top of it. So we have kind of alphabet of machines that we can develop with this system. That imagine how beautiful it will be that with just 80 euros, you can produce, for example, 7 types of machines.
World revolution.
Yeah.
You're gonna be famous. You're going to be famous.
No, it's you too. It's contribution. It's open source world.
We are all going to be famous.
Exactly. Maybe Neil will invite you if he likes a lot of your machine to make a speech in the graduation. Okay. Nothing else that you want to comment that you have questions about? We can consider this session finished.
And just to clarify, this week we won't be able to build the machine. We just design it, right?
Yes, the parts, theoretically, they all arrive The maximum due date they have to deliver is next Friday. But like, believe me, if you can design a machine in just 1 week, cut it and produce it, like say, even if we have the parts in 1 week, I'll be really, really, really surprised. Usually the machine week design takes 3 weeks. This year, as we have on a structured schedule, like it's 1 week for like the teaching class and development, but you have until the end of the academy to finish it. Remember, like, so it's not a 1 week project, but as faster and you can get out of it, much better. Also think smartly, and if you can, you are designing your own PCBs for something, for example, for making a stepper driver, this could already accomplish your output design goal week. So work once, publish 100.
I have a question.
Mm-hmm.
Is it should be a standalone machine? Like, could we just design something like a head for robot or something, like a machine, but it's gonna mount it in another machine?
That question is tricky. Usually, I would say the short question is no. Long question is, if it's a really complex system, yes.
I guess
Let's say in that case, if you are designing an end effector, it should work by itself, even if it doesn't have all the functionalities. But for example, some people design a machine, and they don't design a machine, they make a kind of go-kart machine, like something weird. I think the easiest way and clear example is go through last year's, like 2018, 2017 repos of the machine. In total, there is around like 40 machines per year. So just take a look at them. It's much better. So you can see the kind of projects that you can do. And remember that you need to build a website to publish the documentation and state clearly what is your personal contribution into the good project. For example, let's say Arman and Daniel are working together. Daniel is working on the software part and Arman is working on the hardware part, or I don't know. You need to specify. Sometimes you don't need to do like this, hardware and software. You can define that both work, but what kind specifically is doing each one of you.
And does it have to be a real website or only a repository with markdown files?
It needs to be as your personal website.
Okay.
Yeah, it's a real website.
Yeah, HTML files. Okay.
Yeah. And you need to submit for, let's say, for the final submission of the machine is 1 minute video of the machine working or getting on fire or something. Sometimes gets on fire, to be honest. And the video could be just the machine like end, but usually the most interesting part is like how is the kind of design process. Maybe a few shots on the screen, like modeling, a few shots like assembling, and find the final end of the machine working. Maybe machine is a flamethrower, yeah, for sure. Maybe it's a marshmallow flamethrower. That would be nice. 1 second. Okay. That's one tener el vídeo. Yeah. So that's it. In case we have give you a list of possible hardware. You know that in the lab we have more. Just ask in case you need more. For example, at some point, if someone wants, we have also Peltier cells that can cool. For example, if you are designing the syringe, the paste extrusion, and you want to print chocolate, having a cold platform at 5 degrees will cool down the chocolate faster, and that will help a lot. So we have weird things that you can implement. It doesn't have to be mandatorily a fabrication machine. Yeah, we have recommend you to, because of the main idea of this machine initially is to be a fabrication machine, but doesn't have to be a fabrication machine. Maybe it's just a marble machine. It's also valid.
Coffee machine.
A coffee machine could be perfectly a coffee machine, automatic coffee machine. Exactly. I think 2017, some students of Taiwan lab designing the foot massage machine. So.
Sorry, a what? A food massage?
Feet.
A food feet. Okay, thank you.
A feet machine. Sorry.
I was imagining someone massaging the chicken or the meat. Or
Oh,
Yeah,
like-
that would be nice.
Like Kobe beef.
And marinating it.
Actually, I think usually Japan labs always do food-related projects. For example, the one that did sushi rolls, another one that was making soy dipping for like nagami, like the small rice with the fish on the top, and other ones they do pasta extrusion machine. So Japan labs are usually really good on this one, and they make really funny projects.
Because they have good food over there. Nobody does this in Spain.
Yeah. Hey, make a chorizo maker.
Somebody thought that.
Una embuchadora.
Una embuchadora, like a sausage maker machine. That would be nice.
Amazing.
And you can put it on a lathe and you can sculpt it.
Wow, that would be lovely.
Or a pata cutter.
A lathe for sausages.
A pata cutter.
Hey, nobody comments my reference about the toy.
It could be a barbecue, the machine.
You were bullying the class, Santi.
Could be a self fryer machine. Let's say you have the peltier in the opposite direction and you want to fry things automatically and clean the the meat after it automatically. Like it cooks down, like push it out on the gears and loads more meat.
So many ideas.
Yeah. So just now it's about start thinking and closing up what you want to do. Okay. So let's see you tomorrow.
See you. Bye bye.
Bye, guys.
Bye bye.
See you. Adios a todos.
Thanks.
Thank you.
Bye.
Arigato.
Ciao.
Arigato gozaimasu.